So you may already have done the session on similar triangles, where you are working with three-sided shapes that are identical in what they look like in size of angles, but either larger or smaller than each other, with a common ratio, a common scale factor, multiplying factor that acts the same on each side, either making it, say, 3 times larger for every side or 3 times smaller. The same thing applies to any shape if it can be shown that they are similar, that they are identical apart from their size and proportion. And when you deal with similar shapes, it's not often, or it's not only their sides that you consider. You can also work with their areas and their volumes. So if I just explain this quickly, although hopefully you would have already revised it. If you were to take a rectangle, and let's say this rectangle is 3 centimeters by 2 centimeters, and we wanted to create a similar rectangle that was three times as large, then we'd be multiplying that every side by 3. So you'd end up with a rectangle that was 3 times 3, 9 centimeters high and 6 centimeters wide. So those would be similar shapes because all the sides have been multiplied by the same scale factor. Now, if we wanted to compare the areas of those shapes, the area of this one is 6, 3 times 2, and the area of this one is 54. So the ratio of the areas isn't times 3, because 6 times 3 is 18. Okay, in fact, if you do 54 divided by 6, you'll see that the area ratio is 9 times as much. And the reason for that is because this side has increased by a scale factor of 3, and this side has also increased by a scale factor of 3. So between them, they've increased by a scale factor of 3 times 3, which is 9. So the sides have got a scale factor of 3. The area has got a scale factor of 3 squared. Whatever the ratio is of the sides, it is squared. Now, if that was a cube, so if we had a cube instead, so let's say that was the base of the cube, and it was let's say another 2 centimeters high, then when that is expanded, every one of those is going to be 3 times as big, so the volume will be enlarged by 3 times 3 times 3, so the volume will be 27 times as great in the enlargement as it is in the original. So for the volume, it's 3 cubed. So if you know that shapes are similar and you know their relationship between the sides, then by squaring that will give you the scale factor for the area, or cubing it will give you the scale factor for the volumes. And that's what you have to remember. You work out your scale factor and then you're squaring and cubing, or going backwards, cube rooting and square rooting, depending on what your starting point is. And that's the work that we're going to be doing in order to answer these questions on similar shapes. So mostly this question would come up on a paper 2 where you're allowed to use a calculator, but there are a couple in here where that's not the case. Okay, diagram shows 2 similar shapes. Calculate x and y. So the first thing we do is work out our scale factor. Now, with similar triangles, we were working with ratios. It's easier here just to work out the scale factor straight away. So if we are going from a large shape to a small shape, or let's simplify it even further. Let's work out what the scale factor is as an enlargement. So we're going to do 4.2 divided by 3.6. So 7/6. So if we're enlarging, we're multiplying by that. So to take that shape and make it bigger, we're going to be timesing by 7/6. To go the other way, we need to shrink it, we'd be dividing by 7/6. So an enlargement, multiplying by that, reduction, dividing by that. So x is going to be a shrunken version of 3.5. So we're going to do 3.5 divided by 7/6. So 3.5 divided by 7/6 is 3. So that makes sense, it's smaller. Y is an enlargement, it's going from the smaller one to the larger. And its corresponding side is 3.04. So we can do 3.04 times the scale factor. So, excuse me, 3.04 times 7/6 equals 3.04 times, oh wait a minute, I just noticed it isn't 3.6, it's 3.36. So I'm going wrong here, so let me make these changes. 3.36, 4.2 divided by 3.36, 4.2 divided by 3.36 is 5/4. So the scale factor is 5/4, which is 1.25. So here we're not dividing by 7/6, we're dividing by 1.25. 2.8 centimeters. And here it's going to be 3.04 times 1.25, which equals 3.04 times 1.25, 3.8 centimeters. Okay, so hopefully you spotted that mistake before I did and was shouting at the video. It isn't 3.6, it's 3.36. You find the scale factor, biggest divided by smallest, 1.25. If you're making a number bigger, if you're going in a direction which enlarges the shape, you'll be multiplying by that. If you're reducing the shape, you'll be dividing by that. So x is 2.8, y is 3.8. Number 13, or number next. Dewi's company is planning a new logo. The diagram shows two similar versions of the planned logo. Calculate the lengths of the sides marked X and Y. Okay, so we want the scale factor. So to find the scale factor, you're looking for two corresponding sides that you know, and those are going to be those two. So we're going to do 4.5 divided by 3. 1.5. So the sides in this shape are 1.5 times bigger than the sides in that shape. Or the sides in this shape are 1.5 smaller than the ones in that shape. So x is bigger than that, so x is an enlargement. So it will be the corresponding side multiplied by the scale factor. 1.2, which is bigger, so I know I'm right. Y is a reduction. So we're going to take the larger side and not multiply by 1.5, divide by 1.5. So that's 5 over 3, or 1.67, or 1.6 recurring centimeters. So x is 1.2, 1.6. So those are lengths. We then come to part B. The smaller of the two versions of the logo costs £3.40 to paint with metallic gold paint. Calculate the cost of painting the larger version. So if we're painting that, then what we're dealing with is covering its surface area. So if it's area, we need to square the scale factor. So for area, scale factor becomes 1.5 squared. Which is 2.25. So the cost of the bigger surface is going to cost 2.25 as much, or it's going to use 2.25 times as much paint as for the smaller one. So the cost is going to be 2.25 more because you're going to need more paint. So it'll be £3.40 times our squared scale factor, £7.65. Okay, so the important thing to recognize there is that if you're painting, you're covering a surface. If you're covering a surface, you're working with areas, not lengths. And as I said at the start, that means that you've got to square the scale factor, whatever the scale factor of the sides is. Okay, next one. A company manufactures two different sized boxes. Both boxes are cuboids and are similar in shape. The total surface area of the smaller box is 132. And the length of its longest side is 12. So I'm just going to draw this down here just to help us picture what we've got here. So we've got two boxes that they're telling us are similar, and it's just a sketch, so they don't necessarily look wonderful. The surface area of the smaller box, so the surface area of the smaller box is the total area covered will be 132. And the length of its longest edge is 12 centimeters. The total surface area of the larger box, so again the surface area will be 297. calculate the length of the longest edge on the larger box. So we want to work out the side that corresponds to this. So I've got two areas, so I can work out the scale factor for the area. So we'll have 297 divided by 132. 2.25. So the area of that one is 2.25 times the area of that one. Now I'm interested in lengths, so I want the length scale factor. Now up here we remembered that the area scale factor is the square of the length, so if we've got the area scale factor, to go back to the length we've got to do the opposite of squaring, which is square rooting. And we've already worked it out up there, but you wouldn't have worked that out in an exam because it only comes once. So let's just do it on the calculator to convince ourselves. Square root of 2.25, 3 over 2, 1.5. So that length is 1.5 times as big as that length. Will be 12 times 1.5, 18 centimeters. So a little sketch probably helps. You can see that we've got the corresponding information we've got is to do with area. So we find the scale factor for the area, square root that to give us the length scale factor, and then use that as before. Question 12. Tara has two similar badges as shown below. The front of each badge is coated in gold paint. Okay, that should trigger for us area. The value of the gold paint on the larger star badge is £18.55. So that area relates to £18.55. We want to work out the value on the smaller. So the area of that one corresponds to £18.55. We want to work out that. So the corresponding pair that we've got is length. So we can work out the scale factor of the length. .5 divided by 2.5. 1.4. So this length is 1.4 times as big as that length. Now we need to deal with area because we're talking about the surface area covered by the paint. So the scale factor of area will be 1.4 squared, which is 1.96. So that is smaller, so we're going to be shrinking. So the cost of this one is going to be 1.96 smaller than that one. It's a reduction, so we're going to be dividing by 1.96. So £18.55. We're reducing, so it's a divide by the scale factor. 1.96. So £18.55 divided by 1.96 equals £9.46. Okay, so the scale factor for length, biggest divided by smallest. For the area, we need to square that. Then, because we're reducing, getting smaller, we're going to divide by that scale factor. So £9.46. Okay, this one, non-calculator, put that away. Each length on the larger shape is 3 times the corresponding length on the smaller shape. The area of the larger shape is 90. Find the area of the small shape. So the scale factor for length is 3 times as big. So the scale factor for area will be 3 squared, which is 9. That's got 9 times the area of that one. If the area of the larger shape is 90, that's going to be 9 times smaller. So if we're reducing, we're dividing by the scale factor. So that's got an area of 10 square centimeters. Another non-calculator. Diagram shows 2 similar cylinders. The areas of the ends of the smaller and larger cylinders are 16 centimeters squared and 100 centimeters squared respectively. Given that the height of the larger cylinder, so the area of this one is 16, the area of this one is 100. Given that the height of the larger cylinder is 12.5, find the height of the smaller. So our correspondings are the areas. So the area scale factor is 100 over 16. 100 divided by 16. Now the reason that I've written it like that, and I'm not going to simplify it, is because I know to go from area scale factor to length, I'm going to square root, and that's a pair of square numbers. So the length scale factor will be the square root of that. Square root of 100 is 10, square root of 16 is 4, 10 over 4 is 2.5. Okay, so that's just lucky that I can spot a pair of square numbers. Right, so now that height is going to be 2.5 times smaller than that height. So smaller height will be 12.5 divided by 2.5, which is the same as 125 divided by 25, which is 5. So the smaller height is 5 centimeters. And again, if it's a non-calculator paper, they're going to give you numbers that you should be able to deal with without a calculator. So you spot in your corresponding numbers are areas. So you've got an area scale factor, you square root it to get your length scale factor, and then you deal with that. Diagram shows 2 similar tetrahedrons. So a tetrahedron is like a triangular pyramid. All the faces are triangles. The length of an edge of a larger tetrahedron is 4 times the length of the corresponding edge. So I've got a length scale factor. The volume of the smaller tetrahedron is 3.8. Calculate the volume of the larger. So what's triggering in my head now is the volume scale factor is the cube of the length scale factor. So length scale factor is 4. So the volume scale factor is 4 cubed, which is 16 times 4, 24, 64. So the volume of this one is 64 times the volume of that one. So if the volume of the smaller one is 3.8, just realised you can use a calculator on this one. Just about to go into a complicated non-calculator multiplication, but there's no need. So it's 243.2 centimeters cubed. So the scale factor of length is 4. Volume is 4 cubed, which is 64. So it's going to be 64 times the volume of the smaller one. And the final question. 2 similar rugby balls are shown below. The volume of the larger rugby ball is 500 cubic centimeters. Calculate the volume of the smaller one. Well, the corresponding data that we've got is for lengths. So length scale factor will be 32 divided by 26. Which is 16 over 13. Keep it like that. So the volume scale factor is going to be the cube of that. So power of 3, which let's keep it as a fraction. So 16 cubed is 4096. 13 cubed is 2197. Now, we want to find the volume of the smaller ball, so we're reducing the volume, so we're going to be dividing by that. So it'll be the volume of the large one divided by so we're going to do 500 divided by fraction 4096 over 2197 equals 268.2 centimeters cubed. Okay, so hopefully we've done enough there for you to get into the groove with similar shapes.